Now that we've got an understanding of the various sections inside of a compiled executable and how they are mapped into memory, we can start to look at the actual function of the stack itself within a process and sort of how functions are called. That's going to be important when we get to the consequences of memory corruption. So the stack inside of an execution process is there to manage data and function calls for us. It's a typical stack that you would have studied in your algorithms and data structures course. It's a last in, first out data structure where we track the bottom of the stack and the top of the stack. Typically that's done in a couple of registers like BP for bottom of the stack and SP for the top of the stack. The stack, as we are executing a program, is actually composed of a bunch of mini stacks or little stacks that we call stack frames, where every function will have its own stack frame. It's similar in some ways to the concept of a process having its own virtual address space, so it only needs to concern itself with the contents of its own memory and doesn't worry about the memory contents of other processes. A function is similar in that a function has its own miniature stack and it doesn't need to concern itself with the contents of the stack for other functions. This allows a function to have sort of its own local variables and parameters and to track various states and things like that. Like we saw in our virtual address space diagram, the stack starts at higher memory addresses, and as we push elements into the stack or onto the stack pointer grows towards lower memory addresses. It can make looking at some stack diagrams a little bit complicated, but the more you get used to it, or the more you see it, the more you'll get used to it. So a stack frame, then, this concept of a mini stack inside of the process's primary stack. Stack frames are used as we call nested functions. So I have a function that calls a function, that calls a function, that calls a function. We create for each of those subsequent function calls little mini stack frames. When a function returns, we can effectively destroy or forget about the previous stack frame. We don't tend to actually remove or zero out the contents of a previous stack frame because that would be inefficient and we just don't need to. We can just start overriding previously used stack frames with new content. We don't actually have to manually delete them. Things that live inside of a stack. So the parameters to a function. So if my main function, for example, calls a secondary function, maybe I call printf. All right, printf takes a couple of parameters like a format string and maybe a variable. So I have to push those onto the stack, those parameters onto the stack before I call that function. So then when the printf function begins, it has those parameters inside of its own stack frame. A stack frame is also used to track local variables. So inside of maybe printf, maybe it declares a character and it uses that character variable for various printing operations. That local variable, that character, would live inside of the stack frame for the printf function. Then there's a couple of architectural values that are also stored in the stack. We can imagine that when the printf function finishes its job, it's printed the text, it now needs to return back to main, the sort of main function. We need to be able to reconstruct the stack frame that main was using. And the top of the stack kind of is managed for us in that regard, but we need to remember where the bottom of main stack was. If our BP register was recording or tracking the location of the bottom of my current stack frame, then I need to move it to the bottom of main's stack frame. So we actually store the memory address of the calling function's stack bottom inside of the stack frame for the function that we're in. That will make more sense as we look at some examples, but just know that that's in there. There's a diagram on the next page too. Also, when we return from a function, we need to know which line of code to execute next. So again, if I was in main and I called printf and printf returned, what code do I run next? Visually, we know that we just run the code on the next line after the print statement, but we need a way of communicating that to the CPU. So another thing that is stored inside of a stack frame is the address of the next instruction to execute when you're done the function. Again, we will see that later on. So here's sort of a rough diagram of a couple of stack frames. So let's look down here. We can imagine that we started our program in main. I've drawn the stack the way we're traditionally used to seeing a stack, where this is actually the bottom and we grow up in this direction. So when we begin main, we would actually push on all of the command line arguments to main and the number of command line arguments to main. So those would be in main stack. Think of the next value as kind of where we would return to. It's not exactly that, but there's a value here that manages sort of the cleanup of main. Then we have logically sort of the bottom of main stack lives here. And then as main needs local variables, say main declares an integer called x, x would live right here, right? And then declares another integer called y, and we would push y onto this location. Then say inside main we call printf. Maybe we want to print one of those two variables. So the first thing we would do is push those variables on, or those parameters to printf onto the stack. They start to form the new stack frame for the next function. Then when main actually calls printf, one thing that gets recorded is the next instruction down in main that we would need to execute when we're completing our printf operation. On top of that, we also record the bottom of main stack as the next element in the stack. So we have parameters, where to resume execution in main, and we have the bottom of main stack. So this value would actually point down here. It's a memory address that points to this location. At that point, we begin execution in our, say, printf function, where maybe it creates some local variables, it references the parameters to it, and it does all of its work inside of its stack frame, and it prints code. Eventually, the printf function is going to complete, it's going to finish up, and it will start restoring these values or popping them off the stack and using them. So for example, the bottom of main stack would be popped off and written into the BP register. We've now sort of reestablished the bottom of main stack. The return address would be popped into the instruction pointer, and then we would know where in main's code we would continue executing, and then we would basically return to main, and main would continue with its local variables and doing things like that. So a couple of important CPU registers for organizing all of this content. We have BP that points to the bottom of the current stack frame, typically. That's usually what's held in the BP register. So it doesn't always point to the bottom of the entire process stack, but the bottom of the current stack frame that you're executing in. SP typically points to the top of the current stack frame. And another register I referenced there was IP, or the instruction pointer, sometimes called the program counter. This holds the address of the next instruction to be executed. So as we were popping values off of the stack, we eventually got to this one, the return address in main, that we wanted to continue execution at in our main function. That value would have been popped into the IP register. Okay. So what actually happens when we call a function? We assemble a stack frame. Right, so as I sort of described with the diagram, first thing we do is push the parameters onto the stack. We only really push parameters in 32-bit applications. If we're looking at a 64-bit application, we actually put parameters to functions in registers up to a certain amount. But that's a sort of secondary topic. The next thing we do is to take the memory address of the next instruction in the caller's function. So this would imagine main being the program or the function that's calling another function. So we push the address of the next instruction into the stack. We often call this the return address. You'll see it referenced in some diagrams as RET or RET. RET also being the return instruction in assembly. The next thing the next thing we do is we put the address of the first instruction in the function we're about to call into the IP register, right? So that's where we begin execution in that function at the first memory address of its code. Once we enter that function, that called function saves the previous bottom of this, the bottom of the previous stack frame into the stack. So we're saving the bottom of main stack here. And it actually moves the current bottom of the stack to be the new stack pointer. So we've kind of got a new empty stack since BP and SP are pointing to the same place, and then the function starts to execute. So next we're going to look at a sort of example/demo where we observe the contents of the stack and some stack frames as we step through our simple program. If you recall, it was a factorial program, so there's going to be some nested function calls, so we should see lots of stack frames. In this next demo, we're going to be stepping through our simple program and sort of tracking the stack frames and contents of the stack so that we have a better understanding of how it works during program execution. On the right here, we have a little spreadsheet that's going to be used to view and track the contents of the stack. You can do that. You can view the stack from inside GDB, but sometimes it can be a little bit complicated to read and understand. So to make things easier, we're going to track some values over here as we run through the program. Okay, so I'm going to say GDB quiet simple.out. I'm going to set a breakpoint in main and run the program. So the first thing we want to do is we can have a look at main's stack if we want. Let's print, I don't know, a number of values from the top of the stack. Okay, so what we're doing here, we're going from whatever ESP is right now. We can see the value of ESP by saying info reg. So the top of the stack right now is pointing to FFFF D5A0. So you see that right here. So this is basically a command saying, hey, print me a bunch of values off the top of the stack and interpret them as bytes or as integers rather. So 4-byte chunks. Right? So print me 20 4-byte chunks. So right now that's the value sitting at the top of the stack. And then if you look further down, there's just the contents of main stack. There's not really much in there that we are concerned with at the moment. Because our program hasn't really pushed anything meaningful onto the stack yet. If we have a look at the main function, we'll look for something meaningful that we might be interested in. So actually right now, this is where we are sitting. We're sitting at this call to ReadName, which was sort of the first line of code in the actual C program. Okay, so ReadName doesn't take any parameters, but when we call it, we should see a return address and a new stack frame assembled onto the stack. If we have a look at the code for ReadName, scroll up, the first thing it will do is push the old base pointer onto the stack. Okay. So if we say step I, meaning run the next instruction, we are now in the ReadName function. Okay. Previously, we still have the bottom of main's stack stored in the EBP or base pointer register, and we can confirm that. Well, I mean, that's the value in the register, so obviously we're confirming that. But what should have happened when main called this ReadName function was that main pushed on the address of the instruction that we would return to. If you're not sure what that means, let's have a look at main for a second. So main called ReadName. When ReadName completes, the next thing main did was call ReadNumber. So when we return from this function, we want to go execute this instruction. So this is the address of the next thing to do when we're done with our function. So if we look at the contents of the stack right now, we see this value. That's the same value as that call instruction. So we're just going to save that over here. Okay, and if we go back and just confirm, if we'll scroll up to instruction 56308. 56308. So see, we've saved the address of the instruction we want to run after we're done this function. Okay. So now the function kind of resumes building its stack frame. Remember, the previous instruction pushed the old base pointer onto the stack. Now we should actually see that value in the stack. So there's the saved return address, and then there's the bottom of main's stack. So we're going to record this in our sort of diagram for our stack frame. And then the next thing that happens is that the top of the stack right now, which is indicated by our stack pointer, gets moved into this register to now be the bottom of ReadName's stack. So if we say next instruction, there we see that the top of the stack was now moved into the bottom of the stack. And essentially we have an empty stack now, since the top and bottom are pointing to the same region of memory. Then some code's going to run that needs to run because we're running a 32-bit program in a 64-bit machine, but we can kind of ignore that for now. We know that at some point ReadName is going to call memset, it's going to call print to ask you for your name, it's going to call getString to read in a string, it's going to call print again to print the contents of that string. So I'm actually just going to jump down to the call to print string, okay, or the call to yeah, actually let's first look at the call to printf. Because printf tends to take just a single argument, at least in this instance. All we were printing was the instruction for the user to enter their name. So if we run to this instruction, which it pushes EAX right before it calls printf, pushing EAX will basically take a string that we want to print, push it onto the stack. That way when we call printf, it will know which string to print. So let's go here. Okay, so if I step one instruction, we should now see on top of the stack the parameter to printf. Okay, so there's a memory address there. Kind of makes sense. It's probably the memory address of this string where it lives. We can confirm that by saying print as a string. Right, so we can print the contents of this memory address and cast it into a string. So we see at this address, this is where this string lives. And that's the thing we just pushed onto the stack. So we're about to call printf. I won't be updating this stack diagram over here yet. I'm going to start using this more when we are in our recursive function call to show you subsequent stack frames. Okay, so at that point, we can say next, just to skip over the printf function. It will have printed that prompt for us, and then we would sort of continue with our program. At this point, I'm going to fast forward to where we get to the Fibonacci part so that we can see some nested stack frames. Right to our first Fibonacci call right here. Okay. So now we're about to call Fibonacci for the first time. So now we enter Fibonacci for the first time. So let's have a look at the stack. So we know from last time this will be the next instruction that we go back to in main. So I'm going to save that. So the return address in main. Now we're in our first Fibonacci stack frame. Okay, then Fibonacci is going to save the old bottom of the stack and create a new stack. So we should see this show up in the stack next. So there's the address to return to in main. There's the bottom of the previous stack. So I'm going to save this right here. Okay. And now we're actually inside the Fibonacci function. So we can kind of jump down to here where it's doing the comparison. So it's checking to see if the current parameter is equal to 0 or 1. It says that it was equal to 0, so the jump is taken, right? And that makes sense. Our for loop kind of loops over the values in Fibonacci from 0 through 5 and prints them. So we're actually going to kind of go through this a couple of times. Now we're back in main. I'm going to sort of fast forward to where maybe we're printing or we're accessing like the second or third Fibonacci element. Okay, so I've stepped forward a few times, and now we're probably in some nested call to Fibonacci. Okay. We can see actually how many stack frames we've got right now by saying backtrace. Actually, we're still in, oh right, we are in main. We're about to call Fibonacci from main. Okay, so let's kind of continue with that. Okay, now we're in fib. We should actually see the same contents in the stack frame because the bottom of main never changes and the address of the instruction right after we call Fibonacci never changes. So if we step again, print 2 values from the top of the stack, we see the return address in main, bottom main stack frame, but now we're actually in like a nested version of Fibonacci, or we'll see it calling itself again. So if I say next, here the comparison to 0 shouldn't work because we've got some value greater than 0 as our value that we passed into Fibonacci. Okay. So here the jump is not taken. The jump should not be taken. Now we sort of get ready to do our recursive function call. So here we can actually see that we were at fib of 3. We'll decrement that by 1. We'll push that onto the stack. So basically we're going to be calling here fib of 3 minus 1. So we decremented the value 3 by 1. We now have 2. We're going to push that value onto the stack. So basically we're calling fib of 2. And then we'll do that function call. Okay, so if I step, let's look and see what kind of stuff we have in our stack. Again, first we'll look for the return address in main, which ended in 6349. Here it is. So that's the return address into main. There's the bottom of main stack frame. And then there's some other stuff in the stack right now that you can kind of ignore. So we can say x that was passed in, which was the value 3. So there's 3. That was the parameter to our function. There was the parameter to the function, the return address in main, and the bottom of the stack frame. So I'm just going to clean this up a little bit. Right, so we have the parameters of the function, the bottom of the main stack, or the return address into main, bottom of main stack, and then a bunch of like local variables for this function that we're not really concerned about right now. So I'm not going to record those. But what we are going to look at is now we're pushing on the parameter to our next Fibonacci call. I'll just say param to fib of 2. Okay, this is actually going to be the start of fib2's stack frame. Okay, so if we say step, we're now in the Fibonacci function again, but if we say backtrace, we actually see there was main, then there's the stack frame for the first Fibonacci call, and now we're inside a new stack frame for the second Fibonacci call. We can actually say, if we step through, actually, we'll see where we are. We're about to save the bottom of this stack frame. Okay. So if we look, the contents, the bottom of the current stack frame is right here. So we should see this value get pushed onto the stack next. So we have the parameter to our function, the return address into the Fibonacci function itself that we want to run after we get back from our recursive call. And then the bottom of the previous stack. So we'll update our stack diagram. And just to confirm that this is actually an instruction in the fib function. Right, so we're looking for this value in the instructions. So we know we just did the call to fib of x minus 1, which was this line of code right here, because we subtracted 1, we pushed that onto the stack, and then we called fib on that. And then look at the next instruction. 565562 1c, So this is actually the return to fib 1. And we're going to save the old bottom of the stack frame. So we see all that stuff in there. So we can resume with our Fibonacci function now. Here we're comparing the current value to 0 and to 1. Well, the current value should be the value 2, so neither of these jump instructions should fire. Okay. So now we're going to jump down and call fib recursively on that. So we're going to set up here for our next recursive function call, because fib of 2 should eventually call fib of 2 minus 1, which we'll call fib of 1. So what we're probably going to end up seeing is we're passing a parameter to fib of 1, and that's going to be happening right here. So if we step, okay, we should see that now get pushed onto the stack. A couple of things we also see. We should see the original parameter 3, which is right, that's still down there. We see the parameter 2, which is there, and we see the parameter 1, which we just pushed on. Oops. And this is going to be the sort of our third Fibonacci stack frame. Okay. So we'll step into the third stack frame now. So we see the parameter to fib of 1. We see the return address that our Fibonacci function will return to. So return to fib 2. And then we're going to save the bottom of fib 2's stack frame. Right. And you can hopefully see how this process just kind of continues in this way. So there's the parameter to our function, the return address, and then fib 2's stack frame. Right, and then this fib goes and does its job. If we say backtrace, right, we can see we've now got 4 stack frames. There's main, there's fib 1, fib 2, and fib 3. And we were tracking sort of, well, we weren't exactly tracking main, but there's the stack frame for fib 1, fib 2, and fib 3. So hopefully that shows you a little bit about how we track and manage stack frames inside of a program. As we eventually sort of start to finish our recursive calls, you would just see these stack frames start to go away. You can continue stepping through this program, and it's actually a really good exercise if you continue through or write yourself a simpler sort of nested call program and see if you can actually track these values inside the stack. There will be other values in there, but you can ignore those for now. As long as you recognize the various return values into other instructions and things like that, that's the important part.